basically look at the limiting friction in a couple of places, between couple of surfaces. So that's what makes the problem a little bit more challenging in the case of the three block problems. But at the same time, I think if you have your method well sorted out in your mind, what you're trying to do, and what are the steps you're trying to follow to sort out the limiting friction condition for both the surfaces, then it's just a matter of taking the extra time to solve the question. It's not necessarily very difficult, but yes, it does take a little bit more time to solve compared to the two block problem, because you are checking two conditions over there instead of one condition. So we will be discussing that type of question also today. So, but to begin with, we will discuss an interesting situation. This, I believe, is session number 5 for us in friction. Yeah, so we'll be discussing an interesting type of problem which combines a couple of concepts you've learned earlier in Newton's laws of motion also, along with the condition of limiting friction. In fact, we had seen a similar situation last lecture also, but this is going to be something a little bit more challenging than that question. So this example will involve the concept of pseudo force along with limiting friction. So let's look at this example. So we had seen a problem of this type earlier in the chapter of Newton's laws of motion, but without the presence of friction in the system. Now we are going to incorporate friction in this system also, along with what we'd seen earlier. So we have this triangular wedge which is lying on a smooth frictionless surface. But the surface of the wedge, that one itself now, is going to have friction. So the horizontal floor is still frictionless. This is a smooth floor. This is a 37-degree angle. But this is now a rough surface which has a coefficient of friction of, let us say, 0.4. Okay. And this is a wedge of mass capital M. And on this we have kept a smaller block of mass small m. Okay. And we are going to give the system, starting from rest, we are going to give a system a push in the direction towards the left using a constant horizontal external force. And now again we want to find the condition for the block to be at rest with respect to the wedge. Okay, so let's understand the question in detail. So a block of mass, let's say m equal to 1 kg, is held at rest, or we can say it is, yeah, held at rest on the surface of an inclined wedge or a triangular wedge of mass capital M, let's say 4 kilograms. Okay. As shown, the system is initially being held at rest when at time t equal to 0, a constant horizontal external force is applied, and simultaneously the system is released. So the moment we start applying this horizontal force, we also release the system from rest. We want to find the range of values. Okay, so that means there is a minimum to maximum. So range of magnitudes of f such that the block does not slip with respect to the inclined surface. Okay. So remember, we had done a problem like this in Newton's laws of motion, but there the surface was frictionless. So instead of a range of force, there was a particular value of force for which you had the condition that small m or the block will be in equilibrium in the non-inertial frame of the wedge. But now because there is friction involved, and that too we want the block to be at rest, so it is static friction. So we understand that static friction can take a whole range of values. So that means there is a whole range of accelerations possible for which the block will be at rest with respect to the wedge. And for that range of accelerations, there will be a range of values of force. Okay. So just make sure you understand the question first and then start working on what I'm explaining here. So what you start with first of all is make the FBD of the block in the non-inertial frame of the wedge. Okay. Assuming some acceleration E for the wedge, that is. Okay. Now find the condition for the block to be in equilibrium in the non-inertial frame. Start with this and then we'll understand how to incorporate limiting friction into the case. So once you do this much, that you show the condition for the block to be in equilibrium, you will be able to understand the next step where we'll apply the limiting friction condition. Okay. So start by making the free body diagram. Step number one, which I've shown over here. Start with that, okay, because that is the most important step over here. Okay. So assume that the block and the wedge together are moving with a common acceleration A towards the left in the ground frame. So then get into the frame of the wedge and try to understand what the free body diagram of the block will look like. I mean, what are the forces on the block in the FBD? Okay, what I'm saying is that in the ground frame, assume that this system, this whole thing, is moving with a common acceleration A towards the left. So now, with respect to an observer who's on the wedge, this block will look to be at rest. The block will look like it is at rest. That is the condition. So now what you do is you get into that observer's frame, that non-inertial observer's frame. Okay. So we are in the non-inertial frame of the wedge that is moving towards the left with a horizontal acceleration A like this. Okay. So in that frame, you will see that the forces acting on the block will be first of all pseudo force, okay, because we are in the non-inertial frame. So we will have to incorporate pseudo force into account. It will have a magnitude of small m into A because it is the acceleration of the frame, but the direction will be opposite as you can see over here. And then of course you have a regular set of forces, weight, normal reaction, and this time also friction. This time there is also going to be very important idea of friction. So now the whole question is which is the direction in which friction is going to act. So that is going to be the important thing to consider, and that will actually depend on the direction of tendency of slipping. Okay. So listen carefully what I'm saying here, that this is the inclined plane. Okay. Now, and this is the normal to the inclined plane. So here this angle is theta, and again this angle is theta. So if we assume, so first of all in this frame the block is at rest. So the block is in equilibrium in the non-inertial frame with static friction Fs preventing slipping. Okay. Now we have to understand how static friction is acting, how it's what is the tendency of slipping. Now we have to understand. So here you can see that if mg sin theta is greater than pseudo force cos component, okay, then tendencies to slip is down the inclined surface. Okay, so the tendency of slipping is along mg sin theta. So then what will happen? Static friction will act up the inclined plane because static friction is preventing slipping. So static friction acts up the inclined plane. Okay. But for that, this is a necessary condition that mg sin theta should be okay. So for this condition in this diagram, we should additionally include static friction acting up the inclined plane. Because the tendency to slip is down the inclined plane. So this is the case. Okay. So further, we can understand here that what does this basically mean? This statement, it means that mg sin theta should be greater than ma cos theta. So in other words, A is less than g tan theta. So if we assume the value of acceleration here, so if A is less than, sorry, g tan theta, if the magnitude of the system's horizontal acceleration in the ground frame E is less than g tan theta, okay, then for equilibrium the condition is that static friction plus ma cos theta, that is pseudo forces cos component, together balances mg sin theta. Okay. And normal reaction plus, so normal reaction balances the sum of mg cos theta plus ma sin theta. Okay. So just to make this a little bit more clear, I will make the free body diagram with the forces resolved. Okay. The same non-inertial frame. I'm just additionally resolving the forces. So mg's components will be like this: mg cos theta, mg sin theta. Pseudo forces components on the other hand. Now pseudo force का magnitude ma है, so this component is ma cos theta, and this component is ma sin theta. Okay, and then of course we have normal reaction, and in this what we are understanding is that mg sin theta is dominating over ma cos theta. So friction is coming to the help of ma cos theta. So static friction is acting on this. Okay, so these are the two equations. Okay. So from this, now, so we have got this. Okay. Now, what is our limiting condition friction on friction? Now, the limiting friction condition is that static friction is less than equal to mu n. So on this condition, now we will substitute these two. We'll substitute these two, and that will give us the lower limit of acceleration. That is, what is the minimum acceleration that the system can have such that the block still is in equilibrium. Okay. So just write down up to here, and then we'll see how to incorporate that equation over here. लिमिटिंग फ्रिक्शन कंडीशन होता है ना कि मैक्सिमम वैल्यू ऑफ फ्रिक्शन कितना होता है, म्यू एन. So in general, the friction is less than equal to mu n. Yeah, Ranak, I'll show you the question again, but see, the diagram of the question explains everything that you require here. So just look at the top diagram here and you'll understand what we're doing in the part here. That, you have that block on the wedge and you're applying a force horizontally F from the side like that. Now we have to find the range of values of F so that as the wedge is moving, the block does not slip down the wedge. It remains at rest with respect to the wedge. That is the question basically. So it is a component only ना. वही तो किया ना, component में break किया. Pseudo force ma को we are dealing with an inclined surface, no? So Durgesh, always the normal thing. I mean, the method in a sorry Soham, the method in a inclined plane problem is to break all forces in components which are along x and y axis. X axis being along the inclined plane, y axis being perpendicular to the inclined plane. Yeah, Durgesh, by range, what we mean is not only up to what maximum value, but starting from what value. एक minimum value भी तो होगा ना. If A is less than a certain minimum value, the block will tend to slide down the incline because there won't be enough friction to prevent mg sine theta from making it slide down the incline. Yeah, and I just write down the last part. We haven't solved it yet. Yeah, just a minute. I got disconnected. Okay. So let's go over this once more. So what we're doing is free body diagram of the block in the wedges frame, in the non-inertial frame. So there are four forces: pseudo force and the three actual forces: weight, normal reaction, and friction. Now to understand the direction of friction, we have to first, yeah, Samarth, I'll verify your answer. Okay. Uh, yes, it seems correct. So to understand the direction of friction, first we have to understand the tendency of slipping. So when you look at this free body diagram, it's very clear that mg का जो component है, that's trying to make it slide down the inclined plane. but which component? Mg sine theta. Whereas on the other hand, pseudo force is component which is up the inclined plane, which is which one? Ma cos theta, that is going against mg sine theta. So depending on which one dominates, there's a tendency of slipping. If mg sine theta dominates, the tendency is to slip down the inclined plane. If pseudo force's cos component dominates, it's the other way around. So here let's start with the assumption that suppose mg sine theta is greater than pseudo force cos component. That means E is less than g tan theta. So comparatively we are giving it a lesser value of acceleration because it is less than something. So for lower values of acceleration, the friction acts up the inclined plane, and these are the equations. Friction plus pseudo force cos component is balancing mg sine theta. Normal reaction is balancing the sum of these two. Now on these equations we apply the limiting condition. What is the maximum friction we can get? Mu n. That means the amount of static friction should be less than mu n. So substitute this. So how much is the amount of static friction from equation 1? It is mg sine theta minus ma cos theta. That is the amount of static friction the system is using. But what is the available amount of friction for us? It is mu into n, where what is n? From the second equation, it is the sum of mg cos theta plus ma sin theta. Okay. So from this, we will get a condition on E. Just keep the terms of A on one side, okay, and G on the other side. So you will see cancel off M everywhere, of course. So G into sin theta minus mu cos theta you'll get is less than equal to, take the A on the other side. So we will get cos theta plus mu sin theta. Or if you reverse the inequality for A, we will get the condition that A into cos theta plus mu sin theta is greater than equal to G into sin theta minus cos theta. So this will give us an inequality such that we are getting A is greater than equal to something. That means we are getting the minimum value of A. We are getting A should be greater than equal to this term G into sin theta minus mu cos theta upon cos theta plus mu sin theta. This is one condition we are getting, and from this we are getting the minimum value of acceleration. So this is telling us that A minimum is when this comes with the equality sign. Now just put the values. So the minimum possible acceleration for the no slipping condition is this. So you can take LCM, cancel that off. So we have 3 minus 1.6 upon 4 plus 1.2. So we have 14 divided by 5.2. So this is our E minimum. So E minimum is coming out to be this way. Or we can also just write it as 70 by 35 by 13. So this is the minimum acceleration. Okay. So this is one condition we are getting. Now this is only the lower limit. We have to also get the upper limit. So for that we have to take comparatively larger values of acceleration and see what happens when the tendency is slipping for slipping is up the inclined plane instead of being down the inclined plane. Right, so Samarth, your value was correct, greater than equal to 7g by 26, or that's the same thing as 35 by 13. Now, yes, it's partly correct that when we take the other condition for the largest value, it will just become, reverse of it. It will just become, this condition will just become reversed. So what we can do is just pick up the same free body diagram, but in this we will have to change the direction of friction and also change the condition on friction. So in the non-inertial frame of the wedge, which is having acceleration a like this. Now suppose I assume that the block is at rest in the non-inertial frame such that static friction prevents it from slipping, okay, with a tendency to slip. So tendency is to slip up the incline. Okay, so that means pseudo force's cos component is dominating over mg sine component, and static friction is acting down the incline. Okay, that's how. So now for the solving part, we can, sort of apply a shortcut that everything remains the same, but static friction's direction gets reversed. So just put a minus sign on static friction in the previous. We'll get this kind of thing. So rest all everything is the same. When you look at the forces in resolved form, mg cos theta, mg sin theta, pseudo force is cos component, pseudo force is sine component. Normal reaction up to here, everything is the same as the previous one, but the difference is now friction is like this. Static friction is like this. Okay. So therefore, what we can do is we can just apply a shortcut that here, when we apply the limiting condition, this equation that we had got, we can work with this directly. This equation, we have to just reverse the direction of friction. So I will tell you the trick, and then I'll show you how to get to the trick also. See this that we had now. in this equation we have to modify something, and this is what we have to modify. So this will be the final step when we come to that. Okay. So instead of this equation, we will have to replace this with this. Okay, and we have to replace this with plus mu and this with minus mu. The equation that we should get over here is that A should be less than equal to g into sine theta plus mu cos theta, because wherever the mu was there, it has to be replaced with a minus mu because the direction of friction is reversing. This should become our answer. So let me show you the steps also how this is happening. Okay, but once you get clear with this now, you can use the shortcut method because we're just reversing the direction of friction, and later we are putting the friction as mu n. So that means in my equation, wherever mu is there, it has to be replaced with minus mu because the direction of friction is reversing. Okay, so the equations here will be this: that normal reaction is mg cos theta plus ma sin theta. Mg sin theta plus static friction is balancing ma cos theta, and the condition is that the static friction is less than equal to mu. So again, in this limiting condition, when you put these two equations, you will see you will get this. Substitute these here, you will see you will get this. You will get ma cos theta minus mg sin theta is less than equal to mu into mg cos theta plus ma sin theta. So ये आ जाएगा, okay, which will give you this step. But as I said, I could have got this step by guesswork. This was the condition for A being less than g tan theta. So from this we could have generated this by making this modification. So this was the shortcut trick. And of course here this means that A should be greater than g tan theta. So when A is greater than g tan theta, this is the condition that we have. So from this we will get the maximum value of A. Earlier we had got the minimum value of A. So I'll just give you a minute to go through this and also numerically calculate this. This will give us the range of A. Then remember we have to calculate the range of force. So we still have to calculate from A the value of force. But that is easy because once we've made sure the block is not slipping on the wedge, we can make the combined free body diagram of the wedge plus block. when we calculate this, we will get from here is maximum possible value as that. Okay, so this will become 3 plus 1.6 upon 4 minus 1.2 na aisa. So this will become 46 upon 1.8. So pretty large value of acceleration we'll get. Sorry, 2.8. Yes, that's correct. So that we can write as nearly 16.43 meters per second square. Something like this. Okay. Yeah, 23 G by 14 is also all right. Okay. In terms of G, see this. So now overall we can see if we combine the two statements, we can see that our range of acceleration, this equal to A max and greater than equal to A minimum, where E max we just saw was 23 G by, what was it, 7, 23 G by 14, and A minimum on the other hand was 70 by 26 G. 7 G by 26. Okay. So now from this we can predict about the force. So next is, from this range of acceleration, what about force? Force has to be within a certain maximum to minimum. Okay. So for that, if you just think of the combined free body diagram, because there's no slipping occurring. So combined free body diagram in ground frame, you can see that the condition is equal to m plus m e. So F is equal to 5a. So that F maximum would be m plus m into A maximum. So that would be 5 into 23 by 14. and F minimum be M plus M into A minimum. So that would be 5 into 7G by 26. Okay, so this is an example of a question which incorporates again pseudo force concept along with limiting friction. And because there's limiting friction involved, okay, so there is always an inequality involved, that the range of force can be within a certain range of limits from minimum to maximum, such that friction will be successful in preventing slipping. So if we apply too much of force, then there's too much of pseudo force. So the block actually will tend to slip up the inclined plane in spite of friction. If we apply too little of force, less than F minimum, then it doesn't matter that friction is available to us. It will not be able to prevent the slipping down the inclined plane. So that's where the range of forces kind of concept comes in. Okay. Now next up, we will look at a problem which incorporates limiting friction with pseudo force and also with constraint relation concept, which we haven't seen in some time. So we have this kind of a situation, a block with another block against it. So we have a number of pulleys in our system. So we have all these pulleys attached. These two pulleys are attached to a wall. So they are fixed pulleys. This is fixed to this wedge capital M. And the thread is massless and all. Now we'll take the horizontal floor to be frictionless, but we'll assume there is some friction between the block and the wedge. So this one is a rough surface which has a coefficient of friction mu, whereas this one is a smooth surface. Okay. All pulleys are smooth and massless. The thread is also massless or very light and inextensible. So the system is released from rest with the thread taut. Okay. So find the accelerations of the wedge and the block. So for that, given that capital M is, let us say, 4 times small m, coefficient of friction is 0.3 and g is 10 meters per second square. So start working on this. So again, what we do is FBD of wedge in ground frame. Okay. Assume acceleration a1 horizontal like this. Okay. Then make the free body diagram of block in the non-inertial frame of the wedge. Now assume acceleration a2 like this downwards, but this is with respect to the wedge. Keep that in mind. This acceleration that we're taking is in the wedge's frame, in the non-inertial frame of the wedge. Okay. And solve. Okay. You just have to be a little extra careful about all the forces. Shikhar, there is no relationship between static friction and inertia. Inertia of a body is a measure of its mass. Friction is a type of force. So there is no relationship between the two. The limiting value of static friction depends on the normal contact force. Okay? So the only thing that you can say, the relationship that static friction has with anything else, is that its magnitude has a limiting value or a maximum value of coefficient of static friction multiplied by normal reaction. Now, normal reaction may or may not depend on mass. It really depends on the system. Normal reaction can be equal to weight, it can be less than weight, it can be greater than weight, it can be independent of weight in certain cases. So make sure you get all the forces correctly in this. And also another hint to you is that when you are solving, there will also be constraint relation. Okay, between the block and the wedge, between the acceleration of the block and the wedge. Okay, so hope you people have made the free body diagrams. So let me explain each of them first. So generally you should make a free body diagram as a particle, but here because there are so many things involved, I'm just showing it as an extended body first. So because this pulley is attached to this, so whatever tension is acting on the pulley, that will act on the block. So there is tension, tension, another tension here, then there will be a normal reaction with which this is pushing it, and that one was sliding down. So as it slides down, it will apply a downward frictional force, kinetic friction on this. And of course, the block has its own weight, capital Mg, and the ground is applying some normal reaction on it, let's say N prime. Under the action of all of this, this has an acceleration A1 in the inertial frame, in the ground frame. Okay, this is our capital M free body diagram. So when I convert it to a particle type FBD, so there will be two tensions acting horizontally, one tension acting vertically. Okay. Then there is this kinetic friction acting like this. There's this normal reaction acting like this. Then another normal reaction from the ground, and of course its own weight. Okay. Now for us the concern is only the horizontal forces. So we'll just get one equation from this. And that equation is that 2t minus n is equal to capital M E1. That's our first equation. And as you can see, we have three variables n, t, and E1. Now, for the person standing on this wedge, what he sees is that this block, he sees this block going down at A2 relative to the wedge. Our observer is standing on the wedge, and this is what he sees. Okay, so in the non-inertial frame of the wedge, which itself is having a horizontal acceleration, A1 like this. So on the block in this frame, there is pseudo force acting like this. So mass of the block into acceleration of the frame, opposite in direction. Okay. And of course, apart from this, there is its weight, tension in the thread. Okay. Then this force is pushing it against the wedge. So the wedge applies a normal reaction, and along with that, it also applies a kinetic friction. And under the action of all these forces, it has an acceleration A2 in this frame like this. So we have mg minus t minus kinetic friction is equal to ma2, the third equation. Okay, n is equal to ma1. That's our that's our second equation. This is our third equation. Okay, and of course in this we understand that kinetic friction is mu n. So this equation actually becomes mg minus t minus mu n is equal to ma2, or mg minus t minus mu MA1 is equal to MA2. So this equation becomes this one. So we still have as variables NTA1, A2, 4 variables, and we have 3 equations. So we need one additional equation is required. So where that additional equation will come from? That is nothing but the constraint relation. Okay, there will be thread length conservation or virtual power, whichever you want to apply. So there is a constraint relation. Okay. So additionally, there is a constraint relation which you can understand like this, that now in this diagram, if in a certain amount of time the block moves by some distance x, so how much thread it will release? It will release 2x amount of thread. So L minus 2x, because it will release 2x, plus y, because this will gain this, should be 0. I mean should be L. Thread length should be conserved. Okay. So if the block moves horizontally by x, it releases 2x amount of thread. So the smaller block should move down by y, and with it it will pull y amount of thread length, so that y should be equal to 2x. Okay, so this y is the downward displacement of small m with respect to capital M, whereas x is the horizontal displacement of capital M. So this is your constraint relation. So when you differentiate this, you get the constraint relation between the accelerations. So differentiating this, we get the constraint relation that E2 is equal to twice of E1. So this becomes our fourth and final equation. So this combination of equations has to be solved now. Okay, so you can substitute in this equation, you can substitute n from here. So you'll have 2t minus small m a1 is capital M a1, and then you have this equation. So you can get rid of t between these two equations, and once you've done that, you have a relation in a1 and a2. So just use the constraint relation, you will get the values of the individual accelerations. Yeah, constraint relation, we just think of it like this, that if the wedge moves horizontally by 1 centimeter, how much thread is getting released by it? 2 centimeters, because there are two horizontal lines of thread. So where will that 2 centimeter of thread length go? It will go in increasing the vertical part of the thread by 2 centimeters. So the downward displacement of the block with respect to the wedge y should be 2 centimeters if the horizontal displacement is x. So y is equal to 2x. So differentiate that y and you will get. L is the total thread length, the initial thread length. So this is thread length conservation. This equation here, Prachi, this is thread length conservation. L is length of thread. There's a single thread involved here, so we don't need to use virtual power method. It's very easy to just conserve the total length of the thread. So the two horizontal parts of the thread, their length is decreasing by x. and the vertical part of the thread which the block is joined to, that part's length is increasing by y, whereas the other vertical section of the thread, its length is not changing because these two pulleys are fixed. No? So you can see the two horizontal lines, their length will be decreasing. The vertical line on which small m is attached, that will be increasing, but this other vertical line between the two pulleys, that remains of fixed length. No? So that is how we will understand the thread length conservation. Is the conservation of thread length clear to all of you, or should I explain in more detail if anybody requires? Just ask me, I'll explain in more detail. Okay, yes, Smith. I'll quickly explain. Okay. So see, in our initial diagram, okay, suppose it's like this. So this was our system initially. Okay. Now, after some time, what is happening is that, assume in some time, this wedge has moved from here to here. The wedge is now in this position. So along with that, the pulley is also moved. So this displacement of the block is the same as the displacement of the pulley here, and same as the displacement of this point. So how much thread has got released here? Because the wedge has moved, and now along with the wedge, this block has moved like this. Okay. So this block is moved by displacement of y. So the total length of the thread was L earlier. Now in the new diagram, you can see that minus 2x, because this part here and this part here is gone. But on the other hand, plus y. So this is showing that y is equal to 2x. So now second derivative of y with respect to time, that is nothing but the acceleration of the block with respect to the wedge, okay, e2 in the downward direction. And second derivative of x is nothing but horizontal acceleration of the wedge, like this. So on double differentiation of this, we just have that a2 is equal to twice of a1. Is it clear to everyone now? Yes, Smith, this is clear, beta? Okay. Okay. So this constraint relation, but you have to learn to understand this pretty fast, by just looking at the thread system. So basically the moment you see this system here, you realize that as this system is moving, you realize that this part of the thread length, This is never changing. This part of the thread length, it is changing, it is decreasing. So if it was some L earlier, it is now becoming L minus delta X. This part is also going to become L minus delta X. But similarly, this part is going to change. If it was some L prime earlier, it is going to become L prime plus delta Y because it's going to move down. So obviously, the minus 2 delta X has to compensate for the plus delta Y that has to remain 0. So you have to analyze it fast like this. In the exam, you don't have the time to fully count the thread length with each branch and all that this way. So you have to practice this and get fast at this kind of analysis. Yeah, virtual work method भी आप use कर सकते हो, उसमें कोई issue नहीं. ठीक है. So in the virtual work method, what is happening is that you assume this is moving with a velocity v1. Virtual power you can use actually. So there is tension, tension and tension acting. So power delivered by tension on the wedge, that would be plus 2t v1. Okay. Now this is where it becomes a little bit complicated, that as far as the block is concerned, block का जो ground frame में net velocity है ना, it is not v2. It is the vector sum of v2 and v1. The velocity of the block in the ground frame is actually v1 I cap minus v2 j cap. This is the vector sum of these two. Because remember this minus v2 j cap, no? This is not the ground frame velocity. This is the velocity of the block. Now that you've done relative motion, it is with respect to the wedge. That is minus v2 j cap. Whereas the velocity of the wedge in the ground frame, that is plus v1 I cap. So from that you understand that the net velocity is this. So it is a vector sum of these two. But the tension acting on it is like this. Okay. So the power delivered by tension on the block, okay, that is going to be T acting upwards j cap dot product with the velocity of the block. Okay. So this is going to be T j cap dot product with v1 I cap minus v2 j cap. So as you can see, this will become minus TV2. So this is the power delivered by tension on the smaller block, whereas the power delivered by tension on the wedge is this. So net power has to be zero. So that's why I said that here this method is avoidable because certainly it can create some confusion for you. So net power, this has to be zero. So plus 2tv1 minus tv2 has to be zero. So again v2 is equal to 2v1 differentiated. So a2 is equal to 2a1. Yeah. So this is a small little concept which becomes important over here, that this v2 downwards is the velocity of the block small m in the wedges frame, not in the ground frame. Okay. Okay. So it's basically the velocity of the block relative to the wedge. So that is minus v2 j cap. Okay. And velocity of the block in the ground frame we know is v1 I cap. That is this one. Okay. So now you use this relation that velocity of the block with respect to the wedge is equal to velocity of the block in absolute frame minus velocity of the wedge. So the reverse of this equation actually is that the velocity of the block in the ground frame is the relative velocity plus the velocity of the wedge. So that is why the velocity of the block is becoming this thing. minus V2 j cap plus of V1 I cap. So this is what we have applied to it. This is a concept we have applied. So just go through this carefully once, because obviously this kind of analysis will always help us in future chapters in mechanics also. So you need to understand relative motion and power delivered by a force using dot product and all this. But just for this question, it was not necessary. You could have just done it by thread length. Yeah. Okay. Now, same way now here you can see the vertical tension is not doing work because the velocity is horizontal. Only the horizontal tensions are doing work in the case of the wedge. In the case of the wedge, now you can see that the net tension that is acting, the net tension as a vector is 2t acting horizontally and t acting vertically downwards. But the velocity of the wedge is just v1 I cap. It's v1 I cap only. So that is why it was just 2t into v1. It was not 3t or something like that. So for the wedge, when we have to calculate the power, it is the net tension acting on it, dot product with its velocity. So that just becomes plus 2t v1. So it is not always that virtual power is necessarily the easiest method. Okay, sometimes just, especially when you have only one single thread, so you don't have to count different thread lengths. Just one single thread is wrapped around two or three pulleys. It sometimes it's just easier to just look at the thread length concept and directly get the equation from that. Whereas in many cases you will see that thread length counting will become very complicated because there are very large number of pulleys and more than one thread. So you have to separately conserve the length of the separate thread, whether there are two threads or three threads or whatever. So in those kind of cases, generally you will say that yes, virtual power is the much easier method. Yes, I'll take you through all the FBDs and all again. So hope the both the methods for constraint relations are clear. Now let's go back to solving the equations in the free body diagrams. So what I'll do is I'll just solve the equations here on the side. So I have equation 1 which I have actually converted to this, that 2t minus ma1 is equal to capital M, and capital M was I think 4 times small m, right? So yeah, we had taken capital M was 4 times small m. So I'm going to incorporate that, okay? Now here I'm just solving these equations. So I'm taking this equation, then I'm taking this equation, and I'm going to take the constraint relation. So these are the equations I will need to solve. So in this I will be substituting this because it was given to me that capital M is 4 times smaller. Okay. Then the next equation that I have is mg minus t is equal to, now I can take small m again to that side, and we have mu a1 plus a2. Okay. And we have this equation that a2 is equal to twice of a1. So we substitute this here. So this becomes mg minus t is equal to m into mu plus 2 a1. Okay. And we compare this with this equation that 2t is equal to 5m a1, or just write this here. So, okay. So now substitute this here. So mg minus 5 by 2 ma1 is equal to mu plus 2 ma1. So a1 will become g upon 2 plus 5 by 2, so that is 7 by 2 plus mu. Something like this you should be getting. And a2 is equal to 2a1. Now mu I think was 0.3. So this will become g upon 3.8 because 7 by 2 is 3.5. So that is, yeah, so here shall come to the virtual power again. Yeah, just finish writing down these equations and the solving. I will explain the virtual power method again. So yes. Okay, so hope the solving part is clear to all of you. Yes, Shikhar. See, these are the four fundamental equations we had got. Rest is all substitution. So we are substituting capital N, that normal reaction, as Ma1. Okay. Okay, so I'm just assuming all of you are clear with this. I'll just come through the get through the virtual power thing once more. Then we will talk about the final accelerations of both of them. So in virtual power method, see what we do is we use the concept that net power delivered by tension in the system should be zero. So that means power delivered by tension on the wedge plus power delivered by tension on the block. The sum of these two things should be zero. That means obviously one of them will be positive, the other will be negative. Now let's start with the block. So for the block, you have this diagram here. So yes, if you understand it. So block पे क्या हो रहा है? I mean wedge पे क्या हो रहा है? The net tension that is acting, there are two horizontal components of tension. So 2T like this and one vertical component of tension like this. So the net tension that is acting on it is like this vector. It is 2T I cap minus Tj cap. This is the amount of tension which is acting. Whereas the block is moving in a very simple way. It is just moving horizontally with the velocity v1. Okay, like this. So its velocity is just v1 I cap. So what about the power? The power is going to be power delivered by a force is F dot V by definition. So here it is going to be net tension dot product with this velocity vector V1. So you take the dot product of this and this, you can see it is becoming plus 2T V1. So that is how this term is becoming plus 2T V1. Is this clear, Suyesh? Yeah, Samarth, I'll come back to that. Okay. Unfortunately, right now I've got into explaining the virtual power thing again. So let me just finish this, then I'll go back to that. So, Suyesh, since you had asked the question, I hope this is clear to you, this part. Okay. Now, what about the power delivered by tension on the block? Okay. This part, the power delivered on the block. So, for the block, you have to understand that this is the situation of the block. Okay. The block's net velocity in the ground frame, sorry, in this, there just has to be a correction. This is the velocity of the wedge. So, this, when you add this, you get this. Okay. So, what is the velocity of the block actually with respect to the ground? It is this vector. This is the velocity of the block. It has a horizontal component of v1 I cap. It is coming because the block is pushing it. Okay. But it also has the relative velocity with respect to the wedge of v2 downwards. So its net velocity is this. Okay. Whereas on the block, what about tension acting? There's only one. Okay. So the tension acting on it is just plus t j cap. So what about the power? It is the dot product of these two. So it is that t j cap dot product with velocity of the block. So when you do that dot product, you get minus t v2. So that term is here. So minus t v2. So the sum of these two has to be 0. So from here, we are getting the constraint relation that v2 is equal to 2v1. So that is your application of virtual power over here. So once again, if you are just visualizing this at a very simple level without getting into so much vector algebra and things, okay. But at the exam level, how we can think of all this very fast without making so many diagrams and all this, we can just understand that okay, the wedge is moving like this with V1. उस पे एक टेंशन यहाँ पे एक्ट कर रहा है, एक टेंशन यहाँ पे एक्ट कर रहा है और एक टेंशन नीचे की तरफ एक्ट कर रहा है. So this tension is delivering power plus TV1. This tension is delivering power plus TV1. But this is not delivering any power. So the net tension power developed is plus 2TV1. Now, why? Because this one is perpendicular to the velocity. You can see this line is perpendicular. That's done. Okay. Now, as far as the block is concerned, the block is sitting here on the wedge. With respect to the wedge, it is having a downward velocity v2, but the wedge itself is moving with v1, so it also has a horizontal component of v1. And there is thread attached like this. So how much is the power delivered? This T dot B1 is 0, T dot B2 is minus T. So that is the net power delivered. So now the sum has to be 0. So plus 2TV1 minus TV2 has to be 0. So this is all the working that you have to do actually. Once you get familiar with this concept, this is all the working that you have to do. You can see that this angle is 90 here and this angle is 180. So that's why this net is this. Okay. So when you're thinking of virtual power also, this is all you have to visualize actually. इससे ज़्यादा कुछ करना नहीं है. Okay. So all that is done. Now let's once more go back to the equations. Since equation solving is also a big part of this. Okay. Yeah. So constraint relation, I just explained virtual power method also. But whatever the method of solving, this is your constraint relation. And equation 1, equation 2 and equation 3, they were coming from the free body diagrams. So now all we are doing is solving these equations here. So क्या किया पहले मैंने n को eliminate किया n is small m1. So in equation 1 I have substituted the value of n. In equation 2 I have substituted kinetic friction as mu n, that is nothing but mu ma1. So I've got this equation and I've got this equation. So this is equation 1 only, this is equation 2 only. Okay. But after eliminating n, and then I have incorporated the this thing constraint relation, that a2 is equal to 2a1, that is equation 4 which I had. So I've substituted a2 as 2a1 and then just solved this to find out the value of a1. Yeah, so just go over all your steps once more. Someone. Okay, you should be getting this. Of course, I have also substituted capital M as 4m, 4 times small m. And that was something given in the question. So make sure you understand that. Also, there is one correction. Yeah, here I'll have 5 by 2 plus 2 now. So 5 by 2 plus 2 is 9 by 2, not 7 by 2. So this should come out to be 9 by 2 plus 2. Let's make a correction because you're taking this 5 by 2 that side now. So it's 2.5 plus 2, that's 4.5. So g upon 4.5 plus mu. Yes, Samarth, that is the correct one. So now your answer is matching, right? The same as what I got with the correction. Yes, okay. So fine. So these are the correct values. Okay, and obviously a2 is equal to twice a1. But now last point, which is very important, when we are asked to find the acceleration of the block, the answer is not a2. So that is very important here. The acceleration of the block, small m. What is that value? Remember, we have to find the acceleration of the block in the ground frame. Okay, so that actually has to come like this. It is the acceleration of the block with respect to the wedge plus acceleration of the wedge. Okay, so the acceleration of the block relative to the wedge. वो कितना था, that was equal to actually my a2 in the downward direction. Okay. And acceleration of wedge, of course, we saw was plus a1 I cap. So this thing, so acceleration of the block is actually equal to a1 I cap minus a2 j cap. First of all, it is this. Okay. Then secondly, if I'm asked to find out its magnitude, it is just square root of a1 square plus a2 square. And then you have the constraint that a2 is equal to 2a1 in magnitude. So therefore, the acceleration of the block has a magnitude of a1 root 5. So that is the acceleration of the block in terms of magnitude. And as a vector, it is this. It is a1 into I cap minus 2j. As a vector, you can write it like this. As the magnitude, you can write it like this, where a1's magnitude was what we just saw, g upon 9 by 2 plus mu. This was a1. Okay, or g upon 4.5 plus mu. So that's something you have to be careful about. Whereas the acceleration of the wedge, it is just a1 I cap, so that's fine. So it's a very common mistake that you would mark the option which is showing the value of a2, that is twice of a1. But in fact, the correct answer is root 5 times a1 and not 2a1. Because remember, when you ask the acceleration, it's always the default value is in the ground frame, not the relative acceleration. So that's something to be careful about in a question like this. Okay, people, so hope this is clear. Now, in the interest of extra practice, the most typical type of question in friction is the three block problem. So let us solve another example of three block problem. Though we have done three block problem in the last lecture, but we'll just take a fresh question and go over the whole method once again of solving it. So the ground is frictionless. So these are blocks A, B, and C. This surface is having a coefficient of friction of 0.6, let's say, and this is having a coefficient of friction of 0.4, let's say. G is equal to 10 meters per second square. Mass of A is, let us say, 4 kilograms. Mass of B is, let us say, 6 kilograms. And mass of C is, let us say, 10 kilograms. Okay. So we have to find the accelerations of the blocks when horizontal force of magnitude. Now first let us say 45 newtons is applied to the middle block, to B. Okay. Next, let's crank up the force to 90 newtons is applied to B. Okay. And let's also do a part where a force of 100 newtons is applied to the lowest block. So let's just solve each of these. So the method for solving will be the same like we've discussed in the previous class for this, that the first thing you should do is you should check out what is the limiting friction available to you for each of the surfaces. The contact surface between A and B, just find out the value so that you can confirm it later, or you can compare it later. So find out what is maximum friction available between A and B, and what is maximum friction available between B and C. So that thing you do beforehand, before you attempt any of the parts ABC. Then for each of the parts ABC, you calculate first of all that if they have common acceleration without slipping, then what is that common acceleration? And then you see that for that value of common acceleration, do you have enough friction or not? So to check whether you have enough friction or not, you have to make the individual free body diagrams of two of the three blocks. That will tell you the condition on friction. And accordingly, you know whether your assumption is going to be correct or not. So just try this out, people. So I'll give you a couple of minutes to try out the first part, then I will discuss the solving. I've already told. Okay, so you can see over here that if you make the FBD of A, this is 4G, so this normal reaction 40 newtons. So maximum friction available is mu1 Na, so that's 24 newtons. Then similarly, if you see B's free body diagram, so maximum friction, NB will become Na plus the weight of this one, so that will become 100 newtons. So maximum friction available here will be 40 newtons. And the normal reaction between B and C is not just the weight of B now. Understood? It is the combined weight of B and A now. So we know these maximum frictions. This is 24, this is 40. Okay. Now let's get to work with each of these. So for part A, okay. So if we assume no slipping, that is acceleration of A is equal to acceleration of B is equal to acceleration of C equal to A, suppose. Right? Okay. Then the combined free body diagram of A plus B plus C, there is no friction on the ground, so we don't really need to worry about. So this common acceleration will be F upon total mass. So I'm not saying it definitely has to be this, but this is the assumption. We assume that there is no slipping. So that's going to be 45 divided by 4 plus 6 plus 10. So that is 2.2. Okay. Now let us check if we have enough friction for that or not. Okay. So this is where we will have to look at the individual free body diagrams. So now let's make the individual free body diagram of A. We require only two, but I'll make all three anyway. For solving, we just require the FBDs of two of the three blocks. Now the thing is, the moment I apply horizontal force on this guy, it has a tendency to accelerate forwards. So there is a friction acting backwards here. There's a friction acting backwards here. Tendency to slip is forward now of B. So friction, whereas with respect to B, A has a tendency of slipping backwards. So friction on A will act like this. Friction on C will act like this. So this is also equal to A. Acceleration of C is also equal to A. With this assumption, of course. With this assumption. So from A's free body diagram, we'll see that F1 needs to be mass of A into A. So mass of A was how much? It was 4 kg, and the common acceleration had come out to be, if you can just write this as a fraction, it will be easier. So it's 45 by 20. So 5, so 9 by 4. So only 9 newtons of friction is required. Okay. Now we'll see that that is available because we had seen F1's maximum value was up to 24 newtons. We already checked that. So there is no slipping between A and B. Therefore, no slipping occurs between A and B. Okay. But we still have to check for B and C. So for B, we can write an equation, but more convenient for C, we can write the equation that F2 is mass of C into common acceleration. So how much is F2 required? Mass of C was 10 kg, and the common acceleration was 9 by 4. So that is 90 by 4, or it will become 45 by 2, or 22.5 newtons of friction is required. Now that's also well available to us, because we have seen that F2's maximum value was how much? It was 40 newtons. So this is also fine. So again, we can see that no slipping between B and C also. Okay, and we can just check that all this is correct, because for B the equation should be F minus F1 minus F2 should be mass of B into E. So you can just check here. The value of force that we put is 45. This is 9. This is 22.5. Be 6 into 9 by 4. So you can just check that the values will match. अरे because I am making the FBD of C ना बेटा, ये जो इक्वेशन लिखा है मैंने, ये कंबाइंड FBD थोड़ी है, वो C का इक्वेशन है ना. Understood ना शिखर? You have to consider the mass of the body whose FBD we are making ना. We cannot arbitrarily consider the whole system's mass. When we take the whole system's mass, when we are making the combined FBD, so that's why we have done, that's what we have done here. In this we have done that already. Okay, so now we can see that my assumption is correct. Therefore, assumption of no slipping is true. Okay, and the magnitude of acceleration of A is equal to B is equal to C is equal to, in fact, 2.25 meters per second square. Okay, now just apply the same method to the second part, where we are increasing the force. So there's no need to get confused. You can just note down the free body diagram I've made. The whole logic of Newton's laws and friction application is in FBD. If you are clear with the FBD, there should be no confusion at all. Okay, now let's solve the second part. So in the second part, we've taken the acceleration, I mean the force applied to be 90 newtons, but on block B only. Okay, so we'll take the same approach. F is equal to 90 newtons on B. So let's start with the assumption, assuming no slipping anywhere. Okay, so that means acceleration of A is equal to acceleration of B is equal to acceleration of C equal to E. So again, start with a combined FBD. Okay. So on the system of A plus B plus C, your acceleration will come out to be, so this time it will be 90 by 20, or 4.5 meters per second square. Okay. Now check the individual FBDs. So check for A and C for friction. So everything is same, only the values are different, because we are still applying the force on this only, no? Okay, and we are assuming all three have the common value of acceleration. So for E we will get the equation F1 is this, so it is 4 into 4.5, so it is 18 newtons. So that's still fine because F1 max was 24 newtons. Okay, but on C, you'll see that we'll get F2, so 10 kg into 4.5. So that is 45 newtons. Now we'll see that this assumption is failing because what is the maximum friction available for us between B and C? That was only 40 newtons. So this time we have come to that situation where we know definitely that there's going to be slipping between B and C. They will not move together. Okay. Acceleration of B will not be equal to acceleration of C, but A and B move together. So acceleration of A is equal to acceleration of B. So with this assumption in mind, okay, so F1 is a static friction. So F1 is less than equal to 24 newtons, but F2 is going to be a kinetic friction. So F2's value is going to be mu2 into that normal reaction. So its value is going to be 40 newtons. You can see. Okay. So now you make the individual FBDs once again. Okay. Only this time the acceleration of A is equal to the acceleration of B. But acceleration of C is different. Okay. And this friction acting, its value is 40 newtons. But this friction acting, we don't know its value because it is static friction. Okay. So for A, we have the equation F1 is equal to mass of A into some acceleration. For B, we have the equation F minus F1 minus F2. Now F2's value we know is 40 newtons is equal to mass of B into that same acceleration as A. Okay. Whereas for C, we have the equation F2, which is 40 newtons, is equal to mass of C into acceleration of C. So solving this system, we will get the common acceleration as F minus 40 upon the sum of masses of A and B. So we'll get the acceleration of A equals the acceleration of B equals to 90 minus 40 upon 4 plus 6. So 5 meters per second square. So these two will be moving with 5 meters per second square. But this one will give us a different value. Acceleration of C will be 40 newtons divided by mass of this. So acceleration of C will be 4 meters per second square. So in this case, on solving this is what we are getting, that acceleration of A is equal to acceleration of B is equal to 5 meters per second square, and the friction acting which we can get from this now is only 20 newtons. So you can see that it is less than so this is static friction, but acceleration of C will be 4 meters per second square, and the friction F2 will be kinetic, and so its value will be 40 newtons. So this is the conclusion. Okay. Now you have to use exactly the same method for the third part also, and you try this out. Okay, we are having another lecture this week, so we will discuss the third part. Okay. So this is the common method, irrespective of whether it's 2 blocks or 3 blocks, and whether we are applying the force on the upper block, the middle block, or the lower block. Always, this is the common method of solving the question. You first find out what are the limiting frictions available to you. Then you start with the assumption that if there is no slipping anywhere, then what is the common acceleration? And then from that common acceleration, you check the free body diagrams of required blocks to find out how much friction is needed for your condition. So if that much friction is available, then your assumption is correct. If that is not available, then your assumption is wrong. So you have to change it to slipping. And the moment you change it to slipping, you know the friction acting is kinetic friction. So it's not an unknown quantity, it's a known quantity. Okay, so people, with that, we conclude today's session. Okay. Just go through this last problem in detail and do the third part yourself. Verify it with me on Saturday along with other doubts. So Saturday's session will be for discussion of module questions, and if at all any question is required from HCV, we'll discuss that only, but it will be purely a doubts session. That's it for today, people. All the best.